All right, so I think we're good to go. So today we have another talk related to LLZK and someone also related to a past talk about semantics of MLIR dialects in Lean with with SMT solvers. And so we've got Dan and Ian from Verif who are going to tell us about their work on the verif dialect, I guess, in LLZK, which is an SMT backend for LLZK.
Yeah. All right. So we'll go ahead.
All right, Daniel, you want to? Yeah.
Yeah. Well, you already summarized what we're going to talk about, so let's jump into the why. So the thing with ZK circuits, the constraints are meant for the application itself, and they don't express like its own correctness. So if you write the wrong constraints, you may prove the wrong thing. And the way people try to alleviate this is having documentation on the code, saying like, this is the intention, don't change it if you make changes, have tests, or even go as far as like proving the system by hand, either like actual hand or with some kind of proven system like Lean. And then the last option will be like having a system that automatically takes the circuit you're trying to check and give you the okay or not. The thing with these automated systems is they don't have access to this informal documentation. What they do have access to is some spec that the programmer has to write, similar to what you will do with an automated theorem prover. The two usual ways of doing it is you have a language that you create custom for your application. Imagine you're trying to verify C programs, so you write a specification language that understands the semantics of C. Or the other option is you take a general purpose proving language like Lean and then create a library that helps you define those semantics. And the approach we have taken is the former, and with two main goals. We want to remain independent of possible front-end languages, because the idea is that many ZK languages might lower to LLZK, so trying to cater to all of them will be a mess. And then we also want to integrate with all the rest of LLZK tools. We are the LLZK team, no? So the first thing we're going to talk about is like the top of the chain, which is a high-level language that we have created that compiles down to this new dialect that Alex already briefly mentioned, and then Ian will explain the dialect and what we do with it. So regarding this LLZK spec language that we've created, is a DSL for defining pre- and post-conditions and looping variants for LLZK circuits. And the idea is you will have some front-end or some kind of tool that will generate the MLIR representation of the circuit in LLZK, plus the specification writer that writes in a text file the spec with this language, and the compiler will merge the two into one single IR file, and then can be sent down the pipeline for verification or whatever is down there. No? So inside a spec, what you have is a collection of contracts, and each one target an individual struct or a free function. So remember, in LLZK, we have structs that are meant to represent the main chunks of a circuit, or free functions that are just functions that, depending on the use case, could work for the constraint system or the witness. And a single target, either struct or function, can have multiple contracts associated to them, so you don't have to cram everything into one contract. And the syntax for this is a contract and for, and then the name of the struct. So the compiler will take the IR file given to it and will look for a struct with that name. And if it cannot find it, it will yield an error. Otherwise, it will continue on with the compilation. And inside this contract, and we can define the properties, starting with the conditions. So we have the require and ensure keywords that allows us to define pre or post conditions respectively. And then inside the ellipses, we'll go the predicate or Boolean expression that we need to make sure it holds. So give me a second to drink. Let's do a small example to get an idea of how to define the properties. So let's take this easier contract and let's create a post condition for make sure that the output is an actual Boolean. And in many languages, the type they usually work with is just a felt. So they don't have a Boolean. And let's assume that this is the case for this example. So we will have to check that something is equal to 0 or equal to 1. And in this language, we have strong types, and we have the same types that we will have on LLZK, so booleans, felts, arrays, structs, etc. So what we put here on the gaps we have yet to fill, and we need to pass slides this way, has to be a felt, because we just said that something is equal to either a 0 or a 1. So the only thing we're missing is like the actual output. And in LLZK, the outputs will be defined as what we call like a struct member, which is just a slot in memory with a name. So in the language, while you compile it down, the compiler will look through the struct you're targeting and extract the inputs, the outputs, and give it the names. So in the case of this circuit, the output that we can call out will have like a name that we can refer to. So we just say out equals 0 or equal 1, and boom, then we have our post condition, and the compiler will see all the pieces that needs and emit the final IR. Okay, yeah, and so this out, like I said, is a member of E0 struct. Yeah, I cannot see what's my next slide, so I need to do it from memory. Apologies if I get a transition wrong. So I just talk about members, and we still have inputs, and in the case of free functions, we also have the outputs of the function itself. Functions don't have members. And the thing with MLIR itself is that inputs and outputs don't have names, like we'll have on normal programming language. Like what you see in this at the top here on this add compute MLIR, like IR, is not what is actually used on the APIs. That arg0 is just a convenience name, doesn't have any meaning, and you cannot access that argument that way. So what happens when you have to define on a high-level language meant for a human to write something that is meant for a compiler to work with? Well, we create like these extra meta variables, $arg and $res, for arguments and results, respectively, where you can refer to the nth argument or the nth result to refer to the argument. So this way, imagine that we are going to extend our, for example, now the A0 only works on bytes. So we want to add a precondition that the input has to be within like 256. So in this example, we don't have a name that we can refer to, so we have to use the meta variable to refer to the argument. However, since this IR is meant to come from another high-level language, say Circum, the compiler tool, whatever that emitted the IR, can give it a human-friendly name that we can annotate. So in LLZK, in the case of functions, if you add a property, not a property, sorry, an attribute called function.argname, then the LLZK spec compiler will see that on the AR and bind that name as well as like arg0, such that the programmer that is writing the spec can use the human-friendly name, and things are like now more readable. So this shows like one of the main goals / design restrictions that we have is we want to make things friendly to the humans, hence the extra annotations. But if we don't have them, we have the ways of accessing the information from the IR. Pointer here. So regarding the pre and post conditions, they may not make sense in some contexts. For example, let's consider on the left that now the byte 0 is going to be running on a constraint system that makes sure that the value is a byte using a lookup table. So maybe that precondition doesn't make sense, but it makes sense for the runtime of the witness generator. So we can scope the precondition with that compute block, and that means that if we compile down the contract, we'll get the precondition only for compute and the post conditions for both the constraint and compute. And the same can be done for constraints if we need it. And they can be mixed and matched anyway. So pre and post conditions can be a scope in compute and constraint. So depending on the use case you have, you can precisely specify where you want your things to apply. And then the other property that we want to verify with this system is the loop invariance, right? So here we have a similar problem that we have with the input arguments of a function. We have an IR entity that doesn't have a friendly name that we can refer to. So in LLZK, if you annotate a loop with this loop label attribute, the compiler will find that name, and then you can refer to the loop with the fancy name. So to define properties for a loop, you will do invariant for the name of the loop, and then some loop specific variables that we'll look in a minute, and then inside the block you define their properties. So what happens if you don't have this name because the tool that generated IR doesn't have the label? Well, speaking of missing transitions, I'm sorry. So if you don't have the name, the compiler will just go through all the loops and give them a particular name. So any loop without a name will be named loop n, where n is the nth loop in declaration order. So imagine in the previous example, we didn't have the label. We can still refer to it as loop 1, because that was its position on the list. So again, we have a way of accessing the information we need, even if we don't have the readable name for it. So, like I said, when defining an invariant, we have these extra loop carried values. So in MLIR, everything is single assignment. So when you have something that needs to live through the lifetime of a loop, like many iterations, you pass them as like variables that you pass at the beginning and then when you loop back to the end. So we give them those extra names. In the case of a for loop, we also have a particular set of names referring to the properties of a for loop. So in order, we have the lower bounds, which in this example is that constant 0 operation, then the induction variable, which will be the argument of the body of the loop, then the upper bound, which is a constant 10, the step, which is a constant 1, and then we have the extra variables that we may have. So in this particular example, we just have these iter args, %2 equals %0. That %2 is the value that gets passed through the iterations of the loop. So we refer to it as value in this example. Could be any value, any valid identifier on the language. So if imagine we had more arguments on that loop, we'll have like more arguments on the loop on the right. And if what we had instead was a while loop, we will have just the extra arguments. The 4 arguments I described, like the lower bound, the induction variable, etc., are just for loops. So this gives us the necessary scope for working with the values that the loop cares about. So now we have like the invariant pointing to the loop we were to work with. We created the scope with the arguments. So let's consider this example for a greatest common divisor. What kind of properties can we write for it, for the main loop of that algorithm? So the first one is that we have that a value that monotonically increases or decreases over each iteration of the loop. So in the case of this algorithm, the difference between the two values has to go down. So we can express that requirement saying decreases A minus B. Imagine another algorithm where the value has to go up. We can use the increases keyword. And then the other property we can define is a predicate that has to hold on each iteration of the loop, sort of like an invariant of the loop. In the case of the greatest common divisor, B has to be equal to A modulo B. The thing with the step predicate is that, for example, sorry, there's my train of thought there. So the way, if we just refer to the variable, the way that the equality will read is the updated value of B must be equal to the updated value of A modulo the updated value of B, which is wrong, because it has to be equal to modulo the old value of B. So the way we can access the prior value of a variable in the iterations is with this old keyword, and that way we can refer to the past if we need it for the property we were defining. And inside the parentheses of the old can go any expression. It doesn't have to be just a variable. Okay, so that went through the how to define the properties we want to work with for specifications. But that's not everything we have on the language so far. We also have some extra stuff that makes writing these specifications a bit easier. So the first one is that we can also define predicates inside the spec files. So let's consider an example where we define this predicate. And a predicate is just a function that accepts any number of arguments of any type and returns a Boolean. So the syntax is just predicate, the name, arguments, the brackets, and inside the brackets, we just have a sequence of statements that must end with a return expression. So in this case, we're just checking that X is Plato the philosopher. So we can define this local variable for readability that Plato is equivalent to 1, and then we just check that X is equal to that value. And for completeness of the example, let's just do the same for Socrates. And these predicates can be used from other predicates or from other contracts. So let's use these two predicates to have another predicate that X is a philosopher. And if we have a very simple expression, like just checking out, is it Plato or is it Socrates, we can define a predicate with just one line with the syntax here. This is just a convenience for really short predicates, so we don't have just make things a bit more succinct. And then, so the predicates can be defined on the top level or inside other contracts. For example, we can define word inside the contract. They could also go on other predicates, and they can only be seen on the scope they are. So that teacher of predicate cannot be seen from outside of the contract. And then we just use the predicates to define the properties we actually care about. So for example, we want to make sure we require as a precondition that there exists someone among a set of people that is a philosopher and who has a teacher of assigned the teacher value. And what we just did is 4 comparisons of x equals to either 1 or 2. But since we use the predicates, we wrote it in such a way that it's more readable to the use case that we have here, instead of just the 4 comparisons, which might be harder to understand what's going on at a glance. So that's the main use case of the predicates. Like in any other programming language, just separate things and make them easier to read. And then the last piece there introduces the next thing of the language, which is the existential quantifiers. We have both universal and existential, and they operate over a collection of either a range or an array defined on the struct. Because in the language, we don't have a way of defining arrays ourselves. So that array has to come from the target of the contract. And the way they go is we define the variable that we're going to iterate over in the domain, and then we have a predicate that is just another expression where we check whatever it needs to hold for every or just one, depending on the quantifier. To close like the tour of the language, the rest of things we have for working with circuits, we have normal arithmetic over finite fields, like the kind of operations one might expect. For that arithmetic, we also have Boolean operators, comparisons, and then some that are specific to LLZK. So we have this keyword non-det that says that a value is non-deterministic, which may matter for some properties on the constraints. And then since LLZK has arrays and structs, we have syntax for working with those kind of types, like indexing, member accessing, etc. So that basically covers the language. If you want to go over the syntax more slowly, because in 20 minutes, I know it's hard to get everything. We will have a link to the repo at the end where you can go slowly through the syntax. But the main takeaways that we want to highlight for the language is that we want a high-level language that is easier for people to work with for writing the specs, but that targets the LLIR, the LLZK, sorry, itself, not the many front-end languages that might lower into. So we want to have human-friendly syntax whenever possible, but it should always be possible to access an IR construct even if it doesn't have a friendly name. We are working on this language because this is something fairly new. So some things that we would like to add to it, or we are already working on, is pure functions, because some properties might be easier to define with mathematical functions instead of just predicates. So we want to be able to have functions that may return any type instead of only Booleans. We also want to give names to contracts if desired. And that way we can include contracts within others. This is something that we already have support in the dialect, so you will see, but we don't have it on the front-end language. And then we want to have support for specific with integers, because that's a use case that matters for some use cases, and that will make writing the specs way easier. And yeah, that's all the language. Now I am the dialect.
Yeah, I'll take over from here and talk a little bit about the verif MLIR dialect itself. There's a couple reasons why we wanted to define this both as a high-level language, but then as an MLIR dialect. We're able to compile this high-level language into the verif MLIR dialect. That way we're able to embed it within the same IR module as the LLZK that is being specified. And this allows us to, once we're transformed into this state, we can do shared transformations. Say if we want to transform argument types, to do scalarization passes or specify felt types, we can do that both on the verif contract, like on the specifications themselves, and the IR simultaneously with robust type checking. And also by having the verif dialect as its own dialect, we enable other front ends to be written to specify LLZK-IR. And in particular, we imagine that at some point more languages may develop their own built-in specifications. And so that way, when we compile LLZK circuits from those ZK languages or ZK VMs, we would be able to compile their specification, their native specifications simultaneously into this verif dialect. And the design of this verif dialect was actually inspired by another specification project for hardware circuits, the circ project in the LVM project. So I'll get into kind of a top-down view of how the verif dialect works, starting with basically the entry point operation into verif, which is the verif contract. And these operations are function-like in that they mirror the definition of their target, which is either a free function or a struct target. And so you have a contract that, you know, specifically targets, in this case, the top struct, and it takes in as arguments the same arguments that the struct itself takes in for compute, while also taking in the struct self argument as it would for the constraint function. And that way, the MLIR op has a method of addressing the members within the struct as they've been computed. And so the contract takes this function-like definition, which allows reading in the inputs of the struct target. In order to enable us to write post conditions for the structs or for functions, we also convert the return values of free functions into arguments to the verif contract. And so here, for example, when you're writing a contract for a function that has a single return value, you would add an additional argument to the end of the argument list. And we've built in type checking to the verif contract ops that confirms that you have the correct number of arguments to the function, as well as the correct number of return values or the struct self value. And that way we have a strong correspondence between the SSA arguments, the region arguments between the verif contract and the target of that contract. And this enables us to write complete post conditions for these contracts. In addition to being able to access the function arguments and return values, contracts are able to access the symbols that are available to the target itself. So we have the ability in LZK to write parameterized structs that take in either different parameters or expressions that are computed based on those parameters. And since and using our symbol table lookup logic within the LZK-IR, we're able to have the verif contract look up the symbol tables from the target and identify the parameters that would be available to that target. And not only can they read template parameters, but they can also read the struct members themselves when you're accessing, when you're writing a contract over a struct argument. And in this way, we have strong checking that everything that is accessible to the target is accessible for the contract, so that the contract can write full specifications over everything that the target would be able to natively see itself. One important detail too is that we have in LZK, we're able to write, we have nested structs. You're able to define structs that have structs within them, and those structs may have their own targets. They may have their own contracts and specifications written about them as well. And so since contracts are function-like, they implement function interfaces in MLIR, we also have an include operation, which is a call-like operation, which effectively includes the specification from that sub-target, and you're able to provide to the contract, you're able to specify then the arguments for that contract. So in this case, if I have a struct with a nested struct within it, I'm able to read the inner struct and explicitly include the contract for that inner struct, and I could further impose restrictions on the input arguments to that subcall. And so in that way, you're able to, you can do a variety of different constructions where, for example, I can set within the parent struct, I am able to enforce, perform computation that enforces the preconditions of the sub component within that struct. And so you're able to, if you desire, you're able to write struct contracts that include subcontracts, or potentially you may want to loosen restrictions in this case, and you don't have to call the subcontract. So this allows you the flexibility to either include or not include subcontract calls for including nested specifications for struct members. Going down from there, from the struct and or from the contract level and the include contract level, we actually get into the definition of pre and post conditions themselves. We explicitly encode preconditions and post conditions for witness computation and constraint computation separately. So this gives you 4 different operations: require compute, require constrain, which enforce precondition or encode preconditions to the struct or to the target, as well as verif, ensure compute, and ensure constrain for checking if the those constraints are satisfied by the constraints generated by the target. We do enforce certain preconditions or certain restrictions on the definition of preconditions. For example, you're not allowed to write a precondition that derives from a function result or struct member values, since those are computed within the context of the actual target itself. So it doesn't make sense to write a precondition about something that isn't available at the beginning of the target itself. And the other restriction that we post on these preconditions is that preconditions are illegal on anything defined as the main entry point. In the LLZK we have a attribute LLZK main that defines the main entry point. For example, in CIRCOM, this would be your component main. And preconditions are not allowed because they wouldn't be satisfiable unless they were completely trivial, assert true, because there's no mechanism for computing those preconditions at the entry point. Of course, we also have the loop condition or the loop invariance that we define. And these mirror what Daniel was talking about earlier with the LZK spec invariants there. The syntax of them is very close. These are also region-bearing operations that take in region arguments that correspond, depending on the type of loop, to the special variables of those loop. So for example, for for loops, you automatically get the lower bound, the invariant variable, the upper bound, and the step. And for while loops, you get the input initial arguments for that loop. And you also get the initialization arguments for loops if they have them as well. And within these regions, we have special arguments that are loop invariant specific, just as Daniel was talking about with the increases and decreases operations. Those are restricted to being within loop invariants because they don't make sense outside of loops. And the verif step operation ends up being its own region op. And this allows you to compute expressions using verif old and yield the predicate value that should be true with the verif step yield operation. And so this mirrors the syntax of the LZK spec language fairly closely. The difference being that it now is implemented in MLIR with MLIR syntax. And we do have, we've implemented checking as well here that for the given loop name, it performs a lookup within the target to identify loops with that label, and otherwise it will produce a verification error. We also, to support other features in the LZK spec language, we implemented the quantifier operations as well, both the for all and existential quantifiers that operate over that are able to operate over loop arrays. But instead of defining these specifically in the verif dialect, we actually added these to our existing bool dialect that supports different Boolean operations and Boolean predicates, just because this is not actually, these operations are not actually specific to verification themselves, and these could be encoded for other circuits. And indeed, there are some other circuit languages that have these kind of native existential operations. And so hopefully this will be a useful addition for other languages and other use cases as well. And we plan to continue to add operations as, as we extend the LLZK spec language and as other needs arise for other users of the verif dialect itself. So this leads us to a little bit of what we're actually using or what we plan to use the verif dialect and the LLZK spec language for itself. We've started to work on a dialect conversion from verif into the SMT dialect, which is actually a built-in dialect in MLIR at this point. And we are building a lowering pipeline that allows us to generate the explicit precondition expressions, the target computation expressions, post-condition expressions, and the include calls themselves. And so what I mean by this is what we first do is we take the target for a given contract and we convert that into its own SMT expressions, which compute in SMT the operations that the target are performing themselves. And so, for example, in this very simple struct case, the compute part of the struct target is just assigning the value of the argument to its inner value, and this is represented in SMT by just returning the input argument because no transformation has been performed on that input argument. And then for the constraint function, this is actually creating a constraint or creating an equality expression internally that, given the given the value of the inner value of that function represented just by an SMT int, and the argument to the struct, another SMT int, just computing the equality between the two, because the inner struct here just emits an equality constraint between those two and returning a Boolean expression. And then from there, with the verif contract, we produce different pre and post condition expressions. In this case, there are no preconditions, and so our precondition expressions are simply returning a true, whereas for the post condition expressions, we assert this equality restriction that the inner value and that argument are the same. And then from there, we're able to construct functions that say, given the preconditions, as they do the target conditions hold, or given the target conditions, do the post conditions hold from there. And so we take these verif contracts and break them down into step-by-step SMT computations that we can use to do some proving. And specifically for the subcontracts, we break these down into, as I was saying, the checking of the preconditions based on the input arguments that the caller provides for that include call. And then from there, we're able to compute the target condition and check the post condition of that subcomponent call, given the preconditions that we previously computed. And so from there, we're able to create these calls of the verif include in SMT. There's an interesting gap that we discovered in the SMT support in MLIR itself, in that there's not actually much backend support for the SMT dialect. There's not a good way to, there is no included way to convert this to a solver. So we actually created our own, we started to build our own SMT to SMT libpass that converts our representation of these targets into SMT2 S expressions. And so we're actually hoping at some point to potentially upstream this pass, just because it's not necessarily specific to LLZK or our verif dialect in any way. And so hopefully we can get something like this upstream, because otherwise there's no real native support for the SMT dialect in MLIR itself. So yeah, we've been working on this as well so that we can use it in our tooling. Just as an end-to-end example to show you what we've been able to do, I wanted to talk about a little bit of an example that we've written a contract for, and this was this ED 25519 SIRCOM bug. There was a under constraint bug that was identified a few years ago in this repo that used this simple component, which was less than power, basically try to compute whether or not the input signal is less than a power of 2 given by the base argument. And in this example, the only constraint that's issued for the output, whether or not the input was less than this base power, is that the output itself was binary. And so this was an under-constrained signal because it was not tied to the input in any sort of way. And of course, this repo is now defunct, so this bug is not live anywhere. But just to provide an example of what the actual computation should be, I've included a circuit here that demonstrates the correct computation of this, where you should do a correct bit decomposition and check the bit corresponding to the actual base power of 2 and compute whether or not the input is actually greater than or input to that base. And so we can see here that we have a fairly straightforward under constrained signal bug. And so what we were able to do from here is we wrote this contract in LLZK spec. Basically, it asserts the condition for both the compute and the constraint. So when we have an ensure here, this is an ensure for both compute and constraint logic. And what we're able to do, we use the fairly straightforward pipeline. We use our SIRCOM front end to compile this template into LLZK. We then compile using the compiled LLZK-IR and this specification. We compile these together using the LLZK spec compiler. And this produces a single module for us that contains both the less than power IR and the verif contract representing this, this contract here. We then, running our verif to SMT lib pass pipeline, we converted this to the SMT2 expressions, and then running the verifier, we're able to find a counter example. And for the sake of this example, we just used a base of 2. So basically, is 2 less than the 2 to the second power? 2 is less than 4, which should be true, but we find a counter example where we're actually able to just provide 0. And this is, of course, because of the same under constraint bug that we discussed previously. So using this pass pipeline, we're able to actually invoke the SMT solver to find a counter example given this contract. So I think that's pretty exciting. We do have a number of upcoming work items that we're continuing to work on. We want to continue to add features, as Daniel said, adding more specification features. Some of these past pipelines for converting to SMT and SMT lib are still in review, so we would like to. So we're finalizing the implementation there and merging those into main, and we'll have a release of those when they're ready. We'd also like to add some AI skills as well for deriving LZK specifications, so that not all of these complex specifications have to be written by hand. And so we're just imagining continuing tooling, and if anyone has any suggestions or if there's any use cases that anybody wants to support, we're of course wanting to engage with the community on both of these projects, both the LZK spec language itself and the compiler for that, as well as the verif dialect and the lowering and conversion passes for those. So if there's any use cases that anyone would like to see supported for these tools, any exciting collaborations we come up with, we'd be more than happy to discuss those and add features accordingly. So those are some of the things we're planning and starting to work on. We wanted to give some just kind of as we wrap up the main part of the discussion here, just wanted to give special thanks to the Ethereum Foundation. These two components, the spec language and the verif dialect, were both funded by the second grant that we've gotten for LLZK. So again, just thanks for the, we appreciate the funding, and which has enabled us to work on those exciting projects. And that concludes our talk here. And if there's any questions, we'd be more than happy to take those.
Thank you. Any questions from anyone? Let me look at the chat as well. And obviously, people can feel free to unmute and directly ask questions.
Yeah, and of course, if anyone also has questions that they think of after the talk, you can always get in touch with us on the Zulip channel or Telegram or however else you can think to get in contact with us.
So one question on my end actually is, so you had one example there towards the end. Do you have other examples which are available in the repository somewhere that the people can look at? Because I think obviously you have quite a bit of CirCom now that can go through LLZK, and so it'd be interesting to give the other examples.
Yeah, we don't have a big corpus of examples right now. Most of them have just been kind of handwritten, but we're planning to write we want to have like a benchmark, basically in a benchmark repo of specification examples. We also do have, for the spec language itself, we have its own lit test, which show you how to use the language. We have lit tests for the verif dialect itself. So yeah, we will plan to. We do have a CirCom benchmarks repo, and we would like to add some specification, like a larger array of specifications to that. Yeah.
Nice. And then Francesco in the chat is asking how the counterexample search works.
Right. Yeah. Right now, the counterexample search is fairly simple. Basically, we have a procedure that goes through and says, for the given for the inputs, do we have precondition? Are the preconditions satisfiable? And so we say, given the input, if we for a specification that has preconditions, we say, given the precondition equations and the precondition assertions, are there, is this, negate the preconditions, are they unsatisfiable? And then from there, we assert the preconditions, go to the target, is the target unsatisfiable, and find counterexamples that way. And we do that for the post conditions as well. Yeah, so and some of that is still in progress for efficiency's sake. So we're working on making sure the representation is efficient. So the PR for that is still in review.
Okay, thank you. I think now the questions from me, at least, I think the talk was pretty clear. And so if no one else has any other questions, then we can end it slightly early. And I guess if we reclaim 10 minutes of everyone's time, that's 2 hours. It's 3 hours of productivity for the world.
Oh.
All right, thanks everyone. This will be up on YouTube later, and then there's another talk next week. So see you then.
All right, thank you everyone for coming.
Yeah, thank you for
Appreciate it.
Thanks.